Hello everyone, my name is Minglong. I'm a PhD student in Nanjing University. Today I would like to give a talk entitled Decidability of fully quantum nonlocal games with noisy maximally entangled states. This work is in cooperation with my mentor, Penghui. Let's first introduce the definition of nonlocal games. Which is a core model in multi-proof interactive proof system. Assume that there are two players, Alice and Bob, and are free. The players are not allowed to communicate, but they can share arbitrary quantum states. Once the game starts, the referee samples a pair of questions X and Y from a distribution mu. And then he sends X to Alice and sends Y to Bob. The players reply independently. Upon receiving the answers, the referee determines whether the players win or not according to a predicate V. Both the distribution mu and the predicate V are known to the players, so they can negotiate a strategy before the game starts. We are interested in the value of the game omega star G. It is the highest probability that the players win. Note that nonlocal games correspond to the complexity class MIP star 21. Here, MIP stands for multi-prover interactive proof system. And a star here star here means the players send classical messages and they can share entanglement. 2-1 here means two players, one round. The quantity omega star G is important both in physics and computer science. There is much literature studying the computational complexity of omega star G. We list some of them here. In 2020, the well-known paper MIP star equals to RE resolved this problem completely. It proves that approximating omega star G to a constant accuracy is undecidable, even if the players only share EPR states. We now generalize nonlocal games to fully quantum games. In fully quantum games, the three parties share a tripartite state phi-in. Again, the players are not allowed to communicate, but they can share entanglement. This time, they send quantum messages to the referee. Upon receiving the answers, the referee performed measurements described by a POVM, P win, P loss. Again, we are interested in the value of the game omega QG. Fully quantum games correspond to the complexity class QMIP21. In QMIP, all the messages and the verifier computation are quantum, and the players can share entanglement. Note that nonlocal games, note that fully quantum games are a generalization of fully quantum games. If phi-in can be written in this formula, and the P-win, P-loss are projectors on computational basis, a fully quantum game boils down to a nonlocal game. Here, A, B, R indicates the register is owned by Alice, Bob, and the referee respectively. There is also much literature studying variants of nonlocal games in which either the questions or the answers are quantum. Here we list some of them. Note that fully quantum games are generalization of nonlocal games. So MIP star equals to RE implies that approximating omega QG is undecidable if the players only share EPR states. Now it is natural to ask, what if the players share noisy EPR states? In 2012, the complexity class MIP star was proven to be equal to QMIP. But it does not imply that MIP star with noisy EPR states equals to QMIP with noisy EPR states. In 2021, we proved that nonlocal games with noisy EPR states are decidable. These two results do not imply fully quantum games with noisy EPR states are decidable. This work proved fully quantum games with noisy EPR states are indeed decidable. Let psi be a noisy EPR state, and omega QG psi denotes the optimal value when only sharing arbitrary copies of psi. We write down the formula here. Note that here is a limit here. And the capital phi psi stands for the quantum operations performed by Alice and Bob respectively. If n was bounded, then we can epsilon net all quantum stages and brute force search for the optimal value. So the value is trivially decidable. So our goal is to construct a D such that it suffices to share D copies of noisy EPR states to simulate a strategy using n copies. Here is our main result. This result indicates that it suffices to choose D to be exponential to AB dimension of phi in 1 over epsilon and 1 over 1 minus rho, where AB are the dimensions of Alice and Bob's answer spaces. Epsilon is the error, and 1 minus rho measures the quantity of noise. This work generalizes the framework in our paper in 2021. Here are some differences. First, the answers are quantum. In our previous paper, we use Fourier analysis on Hermitian matrices, and this work we extend it to super operators. Second, the questions are quantum. In the previous work, approximated for each pair of questions and used a union bound. But in this work, the questions are the marginal states of phi in, so we need to find a new approach. And this work has an exponential improvement on the upper bound. Here is our proof idea. First, let me introduce some definitions. Given a linear map phi from the space X to the space Y, the adjoint of phi is defined to be the unique map phi star from Y to X. That satisfies this equation. And the Choi representation J phi is defined as this equation. Because that we want to prove this formula, That is, we need to prove that the D-copy strategy tilde phi tilde psi can simulate the N-copy strategy phi psi. We managed to reduce it to proving this formula. This formula is about the Choi representation. Here, F is some tractable formula. It is necessary to explain why we choose the Choi representation. Given a quantum channel, the Choi matrix, the Choi representation of its joints has nice properties. In details, given a linear map phi from the space X to Y, phi is completely positive, is equivalent to phi star is completely positive, and it is equivalent to J phi star is positive. Also, phi is trace preserving is equivalent to phi star is unital. Here, unital means it maps the identity to the identity. And trace out, it is equivalent to trace out Y from J phi star is the identity matrix. Overall, phi is a quantum channel is equivalent to J phi star is positive, and the trace out Y from J phi star is the identity matrix. The method we use is Fourier analysis. Let's first review Fourier analysis on Boolean functions. First, the inner product of f and g is the expectation of fx gx. Here, x is uniformly distributed from bit strings of length n. For one bit, the basis is chosen to be the identically one function and the identity function. For n bits, the basis is just the tensor product of bases of all coordinates. The Fourier expansion is defined under this basis. We now generalize it to a Hermitian matrix of dimension 2. The inner product of PQ is defined to be 2 to the negative n trace PQ. And for one register, the basis can be chosen to be the Pauling matrices. And for n registers, the basis is again the tensor product of bases of all coordinates. The Fourier expansion is again defined under this basis. First of all, let's introduce some useful definitions. The noise operator with parameter rho is defined in this formula. Here, the absolute value of s on the exponents means the number of non-zero entries of s. And the degree is defined to be the maximal value of the absolute value of s, where the Fourier coefficient is non-zero. For the ith register, for the ith coordinate, the influence is defined to be the sum of squares of Fourier coefficients, where over s, where si is not zero. We can define the same things in matrix space. Note here, the noise operator is just the depolarizing channel. Recall that we want to prove this formula. The idea is to transform P and Q by steps. Here, P is J phi star and Q is J psi star. Each step maintains the following two properties. First, FPQ does not change too much. Second, the distance to positive matrices does not change too much. At last, we will use a triangular inequality. Here we write down the Fourier expansions of P and Q. Here we omit registers from far in and answer spaces because they have bounded dimension and is not important here. P and Q now then have n registers corresponding to the shared states. Here the exponent is n. In details, the first step is smoothing. We apply a noise operator and truncate it to dimension d polynomial. Then we choose a bounded set of registers with high influence. Here the registers in red are with high influence, and the others are with low influence. The next step is to substitute all low influence, all registers with low influence to Gaussian variables. Here, the tensor product is replaced by the dots. This step is called the invariance principle, and whose analog on Boolean functions is a generalization of the central limit theorem. Note that the P2 here is a random operator. And then we reduce the number of Gaussian variables. Note that in the invariance principle step, the number of Gaussian variables are unbounded. In this step, we reduce the number of Gaussian variables to be independent of n. At last, we substitute all the Gaussian variables back to the quantum registers. So in this step, the number of quantum registers of the operator is now bounded. However, the operators are not positive now. So we need the last step. After the rounding step, the operators can represent valid quantum channels. Note that here the number of quantum registers is bounded and is independent of n. So we complete our proof. Here are some open problems. First, nonlocal games with arbitrary noisy states are decidable. Second, are nonlocal games with noisy states decidable if there are more than 2 players or more than one round? Third, can the upper bound on the entanglement be improved? And what is the exact time complexity? As the last one, can we use the framework in this paper to design algorithms for tensored quantities, like quantum channel capacities? That is all. Thank you.
All right. Are there any questions from the audience? Maybe I'll ask one question just to start. So this idea of taking the noise and then taking a truncation of the high Fourier coefficients, it was also in Dorit's talk yesterday morning. It seems like a very useful technique in the presence of noise. Do you have any ideas on other places where it could be used to simplify?
The first smoothing step.
Yeah, just truncating all the high order Fourier coefficients. Right?
Here we use this step to is mainly for the third step, the invariance principle. The invariance principle it needs the polynomial to be low degree. So we need the smoothing step to truncate it.
Okay. Are there questions?
Thank you. I'm going to follow up on that and ask about the noise. So I'm wondering, what's the most important property about your noise? I guess that it allows you to make this cutoff, right? That you restrict to low degree. Do you have a feeling of whether there's other noise models for which you could do this? I mean, right now is this local or global depolarizing noise? I guess local.
Could you please say more slower?
Do you have an idea of other noise models for which your proof could work? So other than depolarizing noise?
Pardon, please?
Okay, maybe in your open questions.
Okay.
Do you have any ideas for the first question? Like, which kinds of noise do you think might work?
Oh, okay. This. In our paper, we can just the states, the marginal states of the shared states are the identity matrix. We wonder if the marginal state is not the identity.
Okay.
Are non games with such states are decidable.
Thank you.
Okay. Any other questions? Maybe if you could explain one more thing. The dimensionality reduction, is that morally some sort of Johnson-Lindenstrauss idea?
Yes.
Okay. All right. Wonderful. Okay, let's thank our speaker one more time.